last time, and today we're going to continue it just for a little while. We're going to look at what's called the fundamental theorem of calculus part 2, and it says if you want to get the area under a curve, which is typically written using this notation, then it's the antiderivative at B, take away the antiderivative at A, and we spent a lot of time yesterday and more time today on finding antiderivatives of more and more complicated questions. So this is the next guy in town. I don't have too many techniques yet, apart from the major one that we've used an awful lot is the power rule. And then after the power rule, it's really just, oh, I know the answer to it because I've remembered that, you know, like the antiderivative of e to the x is e to the x, that kind of thing. But this one is going to be a power rule, but not yet. Is there another way that we could write this that would eventually get us to the place where I could use the power rule?
You could do 4 plus x squared quantity times x to the 1/2.
Almost. What kind of half?
Sorry, to the negative 1/2.
Right. Now, if you distribute this, you get 4x to the negative 1/2, and this guy you get x to 3/2. And I'm now getting deja vu. Did I do this one before? Does this look familiar?
I think we did one almost exactly like this. I'm not sure if it's the exact question.
Well, then I might as well just finish this off then, just in case it's slightly different. So if you add 1 to the power, because you can now do the power rule, you get x to the 1/2. And if you divide by 1/2, it's the same as multiplying by 2, so you get that guy. If you add 1 to the power, you get 5/2, and you divide by that new power, whoops, you get 2/5. And evaluating at 1 and at 4, this fella becomes 8 square root of x, and this fella becomes the square root of x to the 5, evaluated at 1 and evaluated at 4. And what do we get then? We get 8 lots of the square root of 4 plus 2/5 the square root of 4 to the power of 5. Take away 8 square root of 1s plus 2/5 the square root of 1 to the power of 5, which is that guy. This is 2, so you get 8 times, oops, I can't count. 8 times 2, which is 16. 4 to the power of 5 ends up being 2, 4, 8, 16, 32. So 32 times 2 gets you that. Take away an 8, take away a 2/5. You take away the whole numbers, you get 8, and I believe 62/5. Turn that into 40, add it to 62. And if it's not right, it's because I can't count. It's not that the method is wrong. Are we cool with that question? That essentially, you need to convert the original question into individual powers of x, probably fractional powers. Then you can use the power rule. And then I use style points to convert them into what the original looked like, in this case, something like that. And then you can evaluate these and eventually, by the way, it's a 62, eventually you get an answer that works. Okay, I think for the time being, at least, that's the end of that process. Well, no doubt we will, I can guarantee, return to finding areas under curves. But for right now, we are going to look at. Say again?
How did you get 3/2 for the x to the 3/2 when you distributed to the negative 1/2 to the x squared?
Oh, well, I did x squared multiplied by x to negative a half. And basically, when
Yeah.
you multiply things, you add their exponents together. So 2 plus a half is really the same as 2 take away a half. That's like 1.5. And that's where the 3 halves came from.
Oh, okay, okay. I did the math wrong. Okay.
Okay,
Sorry.
that
That makes sense.
okay. Thank you. I like questions. Whoops. So we are going to look at two questions, essentially. I'm going to look at a guy called the area function. And then we're going to look at the fundamental theorem of calculus part 1. And we'll have this section finished when we do those two things. So this is what the area function looks like. I'm going to use the homework question. It's too much work and trouble to try and do it from scratch. The area function is described like this. And you can pick any letter you like. Me personally, I like A of x. Makes me think area, right? So g of x, the area function, is the integral from 0 to x of some function f of t dt. So here is the function. You see it's full of ziggy-zag lines. And the area function is the area under the curve starting at 0 and finishing at x. And we are going to evaluate all these guys. So here goes. G of 0 is a silly question. It's what's the area under the curve starting at 0 and finishing at 0. That answer is silly because there's nothing there, right? You start at 1, you finish at 1. You start at 2, you finish at 2. If you start at 0 and finish at 0, you just got vertical line. There's no area. Right, the next one is G of 5. Right, if you look at G of 5, won't it be the area starting at 0 and finishing here? So won't that be a little rectangle? And so I will just get that area using geometry. 5, because that's what a box is worth, times 10. And 5 times 10, I believe, is 50. So let's get G of 10. G of 10 takes you starting at here and finishing here, right? Now, I could do this lots of ways. It doesn't matter how you do it as long as you get the whole area. So if you start at 0 and you finish at 10, imagine there's a line there. How about a big square and then a little triangle? Would that work? I mean, there's other ways to do it, but that's one of the ways. If you did a big square, it would be 10 times 10, which is 100. And the little triangle that's here is a half of 5 times 10, which is 25. So 100 for the square, 25 for the triangle. I make that 125. So far, so good. Right, now if you want to find 5, 10, if you want to find from 0 to 15, which is here, 0 to here, I'll tell you what, couldn't I cheat a little bit? Couldn't I use all the answers, this guy, and then just add on the triangle to it? So I don't have to reinvent the wheel. Couldn't I use the answer from 0 to 10 and then just get the 10 to 15 bit and add it on? So from 0 to 10, the area is 125. And this little triangle that you're adding on that takes you from position 10 to x to 15 is 5 by 5, 10, 15, 20, is another 50. So I make that 175. And can you imagine what 0 to 30 would look like? So 0 to 30 would finish here. It wouldn't finish there because the scales are 5, 10, 15, 20, 25, 30. So 30 would finish here. What would you do about all this piece of the shape that's below what they're calling the t-axis? What's important to pay attention to when you calculate that area?
It's negative.
It's negative. Now, I'm not going to do it because I want you to get and do some practice. Can we just pretend that that was negative 30, just for argument's sake, right? Then wouldn't the entire area be 145. Now, do you see how it's gone down? Because the net area is the overall area, pluses and minuses combined, and sometimes they cancel out as they would in this case. And that's what an area function looks like. So far, so good. The only one that's not correct is the last one, but you'll have your own version of this question, so you can do the whole thing correctly. Now, on what interval is this function increasing? Well, you might think, well, I don't know what g of x looks like. All I know is some snapshots of what it is at various points. But you can pretty much guess what's going to happen. If you start at 0 and you go x is 1, 2, 3, 4, 5, 10, 15, as you travel along this axis here, isn't the area going to get bigger and bigger? And so g of x will be increasing. But what happens once you get to this point here, which is 15? Won't you then start taking areas away? So when they say here on what interval is it increasing, the interval is increasing from starting at 0 and finishing at 15. And that might look like a coordinate, but I'm using interval notation to represent an area here. And where does it have its maximum value? So if you were imagining calculating the area function g of x, for what value of x, what number along this axis, would you expect the biggest value for the area function to be? We've kind of touched on it.
15.
15.
I agree with you. Do you all agree with that? 15 it is. Right, now here is the sneaky part. Here are 4 pictures of what the area function g of x might look like, but only one of those guys is the right guy. Top left, top right, bottom left, bottom right. Which one of those 4 is it?
Top right.
I agree.
Top
Do you want to? Yeah. Do you want to not argue about it because it's correct, but we want to describe why you went that way?
Because all the other ones, they either start at a positive area at 0 or go negative it at 0. While this starts at 0 and then increases before decreasing.
Nailed it. Yeah. Yeah. Couldn't have said it better. Okay. Well, that's what an area function looks like. Okay. So, unless there's another question to do with that, I want to show you the last piece, which is called the Fundamental Theorem of Calculus Part 1. And it says the following. If you have an area function gx, which is the integral from, it doesn't need to be 0, but very often it is, so we just call it a to x, of some function called f of t dt, right? So there's your general area function, right? The fundamental theorem of calculus says this. That the derivative of the area function is the function. Let's show what that looks like in questions that you're likely to see. There are more complicated versions, but that's the one we're doing. Suppose this is your area function. You're going to be asked to find out what the derivative of the area function is. And essentially what this line here says is that the derivative is that guy. And it's that guy, but with x's. as far as questions go, apart from the fact this is just magic and I'm telling you this is what it is, isn't it very easy to answer these questions? Can you see why the fundamental theorem of calculus part 1 is not that useful? There's not an awful lot you can do with it. Are we comfortable with what the fundamental theorem of calculus part 1 says? It says the derivative of the area function, that's g dashed of x, is this guy here with x's. So we are now going to look at some homework questions to show you what that looks like. And I think one of the weird things about it is that it is so easy you'll talk yourself out of the answer. So here goes. Maybe make this a little bit bigger. Okay, this is I think there are only 2 questions. Here is the area function. Can you see it's going from 0 to x of this guy? Okay, what's the derivative of this fella?
Would it just be square root of x plus x cubed?
End of question. Move on. Nothing to see here. See, some of you were trying to make your life hard, weren't you? Thinking other things or wondering what the heck it was doing. But that's essentially all that theorem part 1 says, is that for an area function, its derivative is this piece here, but with x's. So I guess they've decided to call it g of s instead of g of x. That's no biggie. Does that 4 matter? Not one bit. Could be 0, could be 24, would still be the same answer. So what is the derivative of this guy?
The quantity s minus s to the 6th raised to the 4th power.
Agreed. And you have to use s instead of x. Why do I have to use s instead of x? You see the variable is s this time. The variable was x that time. Oops. I can't do that one, but there's an x on there. Can you see why I didn't bother doing this first? Doesn't it get in the way of finding areas under curves? Because none of what we've just done there really helps directly to find the area under most curves. Agreed? We use the fundamental theorem part 2 version to do all those. And that's the important one. That's the one that actually is useful, in my opinion. So what's next? Well, our next section, whoops, coming up. It's going to be called, let's get the right number for it, it's going to be section 5.4. It's going to be called indefinite integrals. We've actually done quite a few indefinite integrals. I don't think I called them that. I'm pretty sure I called them antiderivatives. So we're going to get into this in a little bit more detail, but let's give you a quick warm up of what an indefinite integral is. First, a definite integral. That's what we did yesterday, right? How you find the area under a curve, but it's called a definite integral. Divided by 3. And it's called that because don't you know the numbers from 1 to 3, right? You know you're going to start at 1, you're going to start at 3. In this case, you would add 1 to the power, divide by the new power, evaluate at 1, evaluate at 3, 3, 9, 27, that's 54, take away 2. Can you trust me? The answer's 52. Don't want to dwell on that too long. That's what a definite integral looks like. Here is virtually the same question. An indefinite integral has one difference between that and the earlier ones. Do you notice that there's no limits of integration? Right, you don't find from 1 to 7 or 2 to 10. It's totally left blank. When that happens, you are calculating an indefinite integral. You still use the power rule, but you add C. Remember our arbitrary constant that we kind of started with, then we pretended you didn't need to use them, and now he's back again. So in a lot of ways, don't we already know how to do these questions for the most part? We just don't plug in numbers anymore. We plug in plus C. And in a funny sort of a way, I think they're easier to do because you've less number crunching. In fact, virtually no number crunching, right? You don't have to find out what the square root of 7 cubed is and things like that, right? You don't have to do what, you know, numbers like that. You're just going to write down what you've got and you call it good. Now, before we get into the swing of these things, and we're going to use the same techniques that we used earlier, is that I'm going to create a table. And it's typically called the standard integrals. So I'm going to have a function, and then we're going to have its antiderivative. What is it sometimes called now? It's integral, which is actually what it tends to be called mostly. Now, this is a repeat of information. Some of it is anyway. In this case here, this is the power rule. Don't you add 1 to the power and you divide by the new power. That is the power rule. So I'm going to start chucking in guys that we did a couple of days ago. Well, maybe Friday probably. And see if we can remember them all. How about 1 over x? Antiderivative of 1 over x.
Natural log of x.
How about some trig? No, not yet. I forgot my friend. E to the x. The nicest function in the world. What's his
It's
integral?
just e to the x.
Dead easy, right? I like that one. Right, let's do some trig now. I'm going to do a sine. I'm going to do a cosine. I'm going to do a secant squared. And I'm going to do a secant tan. Okay, and integral of sine x. Be careful.
Negative cosine x.
Correct. And so the integral of cosine is positive sine x. I can't remember if I did secant squared. If I didn't, this is us doing it now. And it's one of those standard integrals. That is things you just need to memorize, I guess. Right? That's what this is.
Is it tangent?
It is. It is tangent. And I'm 99% sure I didn't do secant tan. Can anybody here tell me the antiderivative of secant tan?
Secant.
Nailed it. Well done. I wasn't expecting that one because it's a pretty rare one. Are we good? Right. Now, let's put some I do know that we did these. at least I did these with one of my two calc classes. Maybe I didn't do it with you.
The first one is inverse tan.
Agreed. What's the second one?
Inverse sine.
Nailed it. Those are, well, that one definitely is very rare. This one you've probably seen a few times. I think the secant becoming secant tan and backwards, right? This one is a little bit on the rare side, but it does happen. And I just left enough room. That represents 5 to the x, 10 to the x, 2 to the x, right? So it is not a power rule. You don't add 1 to the power and divide by the new power. That is not how you get its antiderivative. Its antiderivative is that guy. But it is more than just that guy. What else? I'd be amazed if you remember this, because you probably only saw 2 to the x maybe in 1 or 2 questions, right? When you did differentiation. That's the only place it would come from. Last chance, I think it's about unfair to ask you, but you've been so good at the others, I thought it was worth a shot. Over the natural log of A. Now, these standard integrals are considered the ones that we would expect you to have memorized and know, right? You just know that the integral of secant squared is tan, right? There's no proof or anything that you're doing, you just know it is, and that's fine. Like you know e to the x is, right? So these are going to, from time to time, these are going to appear in what we're about to do. So let's do some indefinite integrals then. Three x squared plus 1 all over x dx. Think of what we did in the definite integral world. And we definitely did something like this earlier. Maybe Monday, I think it was Monday. Where do I go? I have to do stuff, right? I can't
Would you
do it now.
bring the x from the denominator up to the numerator and have it the quantity 3x squared plus 1 times x to the negative 1?
You would. Isn't that what we did to a similar question on Monday? Do not think about changing your method just because there's no numbers here. Do exactly the same algebra, whatever it is you did in these questions as you did with the other ones. Now, if you multiply this out, 3x squared times that guy gets me 3x. And this guy here is a little bit of an issue, because I am not going to leave him in that form. Normally a negative power is fine. You know, x to the minus 4 is totally fine. In fact, that's a good way to leave it, because then you can do the power rule on it, right? And x to the negative half is fine. You can do the power rule on it. Don't try to do the power rule on x to the negative 1. Remember how weird that gets? Add 1 to the power, you get 0. Now you have to divide by 0, right? It doesn't work. If you write this guy as that, I may give you a clue to where we're off to next. Power rule. Add 1 to the power, divide by the new power. And 1 over x is?
Natural log of x.
And then remember to add your plus C. WebAssign is very unforgiving in these questions. You need to put in that plus C or it will tell you you're wrong. And you might not even notice it, and you might spend some time, you know, doing other stuff when you didn't need to. All you needed to do was add a plus C. How about,
Quick question.
yes,
Does WebAssign care if the C is capitalized or not?
I don't know,
Okay,
but you'll tell me tomorrow, right?
I guess I'll find out.
It did in Calc 1 in my experience, so I would at least try personally. That's just like at least what
What,
happened
try a
with me.
capital C?
Mm-hmm. That was just
Okay.
at least what happened with me personally with Miss Briggs's class, but I don't know.
Yeah,
You
I always
might,
just
I
put mine
just
as
a
a.
thought.
Yeah, I always just put mine as a capital
Okay.
C just in case.
Right, that's the decision then. Everybody use capital C. That cures the issue. We've done one like that before as well. We just had numbers on it. It's all about what you do first, what you do second, right? There's a process here. You have to do something before you can do the next thing. What's the first thing I need to do on this fella?
Need to FOIL out first.
Okay, so you're going to get 6x squared minus an x minus a 1. And now isn't it just a power rule? So what will that get me? X cubed divided by the new power minus a half x squared minus an x and plus a capital C. Aren't these a lot quicker than the ones we just finished doing? Because you don't have all this plug in this number, plug in that number, subtract them, try and make it look pretty. A lot of that is taken, you know, we don't need to worry about it because it's taken away from us. We don't need to do it. Any questions so far, or does this actually seem to be just more of the same? Right? Major difference, you don't deal with numbers, you stick a plus C. I mean, if I was summarizing, that's pretty much it, isn't it? Do what you were always going to do, but don't plug in numbers, plug in a plus C instead. Right. I'm going to go and see if I can load up the homework for this. That way I can just kind of talk through some of these questions, I hope. Oh, timed out. What do you mean bad request? You know, sassing, frassing. I'll be a few more minutes. I'm hitting buttons all over the place trying to get this thing to load up. Oh, go figure it, loaded up. Okay, so indefinite integrals is section 5.4, got it. Hit view, bring it over here, looks good. Right. Now, where have you lot gone? Oh, there you are. So we're going to show you, where the heck did that go? Excuse me. Why is that that? That's not right. My machine is being a pain in the butt right now. There we go. There, are you now looking at homework questions from 5.4? Did you notice how good I was at not swearing there? You all should have been impressed by my self-control. I did not swear once. I believe there is a math professor, who I will not mention his name, who is notorious for not being as self-controlled as I am when things like this happen. And you may or may not have had that professor. Now, I'm just going to show you these questions, talk through them a little bit, and then actually do them. Because what's going to happen here is they're adding all sorts of complications to the basic puzzle, right? So let's start looking at question 1, maybe make that a little bit bigger. Now, I'm not going to get into the specifics yet. When you look at question 1, doesn't it look really weird? X times 2 cube root of x plus 7 fourth root of x dx. My strategy for doing that question is to turn the cube root into x to the third and the fourth root into x to the quarter. Then I would distribute it and it would be the power rule. Don't need the details. How do you think I would tackle question 2? Because I got to fix it. It's no good right now. Any ideas how you would approach it? I don't need the specifics, but in general, how would you approach question 2?
Get rid of the secant squared at the bottom first.
And what would that turn into?
Yeah.
You're right, Michael. What would that turn into?
Yeah. Well, after we differentiate, it'd be a 10x, but I'm not sure.
Oh, I see what you're doing. No,
Yeah.
I got you, but no. You can't integrate fractions like that. I wish you could. It would make them really good.
Oh no, that's not what I'm saying. I mean, you'd have to multiply everything by secant squared, and then after we go through everything, we change everything into what we need to. But
okay,
yeah, I'm just jumping ahead.
Right, that's fine. The secant squared is 1 over cos squared. So if you multiply top and bottom by cos squared, you'd have essentially the same effect. Question 3 is it's a cool question, and I definitely will do question 3 for you. You deserve a bonus prize. You deserve money if you can figure this one out. I'll give you about 10 seconds to think about it. Technically, these are not indefinite integrals, but it doesn't change the question. Right? Last chance. Anybody got an inkling to what on earth that's going to be like? Factor t to the 4 minus 1. It's a t squared plus 1, t squared minus 1. The t squared minus 1s cancel, and it ends up being 1 over t squared plus 1. It ends up being an inverse tan. Now, technically speaking, those questions are definite integrals. So here's our first indefinite integral. You're not even being asked to do anything except to say that that is true or that is false. And it says you're going to do it by differentiation. And you might think, wait a minute, we're integrating. How can I check something by differentiation? Well, what you need to do is differentiate this guy. And if he equals that guy, you will say true. And if you differentiate this guy and he doesn't equal that guy, you will say false. Question 6, much nicer to do. Isn't that just an ugly power rule with ugly decimals? Question 7, isn't that a nicer power rule with nicer looking numbers to do it to? But it's no algebra needed, it's just power rule. Oh, and remember your plus, oh, there we go. Use your plus C. It looks to me like it's a capital C in the instructions as well, isn't it? So when we decided plus C, that's a good idea. Power rule, power rule. What's this guy? What's the integral of 2 over x squared plus 1?
Is it 2 inverse tan?
It is, it's in my list. 9, multiply that out, and you get some nice guys that are in your standard integrals. You get a secant squared and a secant tan. Would you agree this one is just basic? That's a sine x, and isn't this a power rule? Right, nothing special. Nothing to see here. Oh, they put in a number just to be awkward. So they've made a definite integral again. Ooh. Forget about the root 2 over 2. We'll worry about that in another day. What is the integral of that 1 over the square root of 1 minus r squared? Because it is in my list of standard integrals. 1 over
Is that
the square root of 1.
inverse sine?
It is, in this case, inverse sine of r, because the letter is r. There's some puzzle questions, and we are done. So I'm now going to return back to that question 1. And if they give you numbers, then you have to do the whole thing, right? And if they don't give you a number, then it is an indefinite integral, and you do a plus c. So, oh, good grief, time. Didn't realize what the time is. Okay, I have enough time to do this one example. And then when we come in tomorrow, we'll start doing more and more of these guys. So it's the integral from 0 to 1. It's going to be an x, 2 cube root of x plus 7th 4th root of x. And what I said is that if you're going to do this, you need to rewrite the cube root as a 1/3 power, and the 4th root as a 1/4 power. Now you multiply these together, you add the powers. So 1 1/3 becomes 4/3, and 1 1/4 becomes 5/4. And now you can do the power rule. Yikes. 4/3 add 1 gets you 7/3. Divide by 7/3 is the same as multiplying by 3/7. So that's where that came from. Add 1 to 5/4 and you get 9/4. Divide by 9/4 is the same as multiplying by 4/9, and that's 28/9. And that's the antiderivative part done. And then you do evaluate from 0 to 1. This fella becomes the cube root of x to the 7. And this second guy becomes the 4th root of x to the 9. So I just did some style points there. Actually, since these numbers are dead easy, I can do this in my head. It's going to be, isn't it going to be 6/7 times 1 plus 28/9 times 1? Because isn't the 4th root of 1 just 1? And isn't the other two guys just going to be zeros? So I won't even write them down. 0, 0, big lot of 0. So these two guys have to be changed into God in Himmel. That's why calculators were invented, right? So on my TAI 84, here goes. 6 divided by 7. Add 28 divided by 9, and you get that ugly guy. If you hit the math button and do number 1, it should change it into a fraction. And not only will it change it into a fraction, it will even simplify it for you if it needed to. Now, isn't that much easier than trying to do it in your head? So if you come across some really ugly fractions, just add them on your TI-84. Hit the math button, and choice number 1 turns all answers into fractions. Are we good? Right, say hi everybody and for attendance, and I will see you all tomorrow. I will hang about if there's any questions between now and then.
Thank you.
Oh, do you all know what day your test is?
Monday?
Nope, it was Monday,
It
but I
was.
changed it.
Okay, good.
What day is it now?
Is it Tuesday now?
Yes. Why did I have to cancel Monday?
Holiday.
It's a holiday and I didn't realize when I was doing my schedule. So you have Monday off. So don't worry, I'm not going to ask people to come in during their day off. So Monday is just off and Tuesday you'll do your test. Okay, that's it. Bye-bye.
Thank you. Bye-bye.
You have a good day.
Thank you.
You too.
A quick question, is Wednesday still a regular day? I believe it's inauguration day, but it shouldn't affect our class schedule, right?
It has no effect on our schedule. You're right. It's just a normal day for us.
All right, thank you.
Okay.
I had a quick-
Monday is a holiday. I think
Mhm.
there's another holiday like 3 weeks later where I had to move the test again because it was a Monday and Monday's a holiday.
I had a
Any
quick
other
question
questions?
on the homework?
Sure.
For the
Which one?
secant, the one with, no, it's question 2. For the secant squared,
Oh, okay.
which one? It's the one with secant squared theta in the denominator. I know you went over it, but I forgot.
It's not.
How do
It
you-
is not theta, by the way.
Oh,
It's
what's it called?
theta.
Oh, theta.
You,
Okay.
yeah, you got to remember to stop saying things the way Americans say things. The correct name of
Yeah,
that
sorry, I
is
kind of have a
theta,
habit of doing
right? Yeah, I can understand. Being American, it's easy to fall into that mistake. So anyway, what was your question?
that. I know you went over it, but I
How you do this?
forgot. Yeah, how do you bring that up? for
Well,
the-
I verbalized it. Not everyone is, an auditory learner. So you're getting a kind of heads up on what this is going to look like. It isn't secant squared 1 over cos squared.
Yeah.
Agreed?
Yeah.
So when I bring it to the top, it turns into cos squared theta. So I'll try and show you where that's
Oh.
coming from.
Okay.
1 over secant squared is 1 over cos squared. In other words, the reciprocal of it.
Mm-hmm. Yeah, so you just multiply it. That makes sense.
Right. So I'm going to multiply these guys out. While I'm at it, well, let's do it in order since I said that. I'm going to do this guy, cos squared theta, plus 2 sine theta, cos squared theta, tan squared theta. And sometimes you have to trust the math here. It looks like I've made it worse, not better. But hold on here. I can still do a little bit more and something really nice is going to happen. Can't you turn tan theta into sine theta over cosine
Yeah.
theta? And so tan squared will turn into a sine squared theta over a cos squared theta. And then, kind of like magic, they cancel out. And now we've got 3 sine theta cos squared theta plus 2 sine and sine gives me sine cubed theta. And again, you're going to say, well, great, I'm still stuck. No, you're not. You have to look at, is there anything that you can do like a common factor between these two guys?
I mean, I'm not sure because like one is cubed and one.
Right, but can't you at least pull out a single sine theta?
Oh, yeah.
Bit like I've got an x and an x cubed. I can at least pull out an x, right? So I'm going to pull out a sine theta. And I just made a mistake here. That's a 3. So that's a 3. So for some reason it turned into a 2. I have no idea why. So it's a 3. So can't I pull out a 3 sine theta then? And that's cos squared theta left over. And if you use up one of
And
these,
sine
is
squared.
it not a sine squared theta?
Oh, and then, yeah, that turns
Right?
into, what is that again?
Just one.
That's
One.
one.
Yeah. Sine squared plus cos squared is 1, but cos squared plus sine squared is the same thing, so it's also 1.
Okay.
So that's 1. So you just get 3 sine thetas times 1, which is this. Oh, we know how to do that, guy. And you're finished. Well, you plug in some x's, but I've given up writing those down.
Okay. Yeah, that makes sense now. Thank you.